Let's now look at some examples of evaluating limits, but now I have the function. So here in this first example in part A, I have the limit as x approaches -2 of x squared plus 5x. So I'm going to show you how to use those limit properties that we just talked about, and then you'll say, okay, well, geez, that's a little long. Can't you get me something that's a little bit easier? And then we'll talk about a shortcut to deal with this. But we're going to show the long way first here. So first I'd say, okay, well, limit as x approaches -2, I've got x squared plus 5x. I can take this limit statement and I can apply it or distribute it over addition and subtraction. So I can say limit as x approaches -2 of x squared plus limit as x approaches -2 of 5x here. Then you'll say, okay, well, I really only know how to deal with x, right? I don't know anything else about these other functions. I guess I could graph them, but who's got the time for that? Not me. So I'm going to use my limit properties. One of my limit properties said, you know what, you can take this limit and carry that inside of this power right here. So I can say, you know what, instead let's look at limit as x approaches -2 of x and then square the whole thing. Plus over here, the second term's a little bit easier to deal with. We just have this constant multiple of 5. So I'm going to go ahead and factor that out here. So I'll have 5 times the limit as x approaches -2 of x. And so my goal here has just been to break this down so that I just have the limit of x, because that's something that I know how to do. Remember, if you go back and look at those limit properties, the second one said, you know what, if you just have the limit of x, you can just go ahead and plug in the limit that x is approaching, which in this case is -2. So I can say, okay, this is really -2 squared plus 5 times -2. And then from here, we've got a little bit of arithmetic. So -2 squared would be 4, plus 5 times -2 is -10, which would give me -6. So sure, you could absolutely do each problem that way, but it seems silly, especially if you have something more complicated than a quadratic, right? If you have multiple terms, if you've got a lot going on, if you have a really complicated function, this process is going to be, it's going to take a lot of time here, and you're going to have to know those rules forwards and backwards. But luckily for us, we have this theorem that says if f of x is a polynomial or rational function, and even some radicals too, and f of c is a real number, then limit as x approaches c of f of x equals f of c. So this statement right here is really what we're interested in. It says you can evaluate the limit, so this says you can evaluate the limit, which is this piece right here, by just taking that number that x is approaching and plug it into your function. So for the most part, for the vast majority of the functions we're working with, you can just take that number and plug that into your function, and hey, that's your limit. So if I wanted to use that shortcut here, let me do that. Oh, let's do that in purple. How about this? So if I wanted to take a shortcut through this problem, if I wanted to say limit as x approaches -2 of x squared plus 5x, I can try taking -2, plug it in. As long as I end up with a real number, that's my limit. So here, this is a polynomial. It should not give me any problems. I'm going to take -2 and plug this in for x. So -2 squared plus 5 times -2. -2 squared, I've got +4. Remember, be careful with this guy if you're using a graphing calculator. If you type in -2 squared without parentheses, and let me just do an aside over here. -2 squared, this really actually says the opposite of 2 squared. So it's going to square 2 and then apply the negative. So you'll have -4 versus -2 squared. That'll get you the right answer of +4. So just be careful if you're using a graphing calculator at home. And then 5 times -2, of course, that's going to be -10. 4 plus -10, I've got -6, which is exactly the same answer we got earlier. So that works out really, really nicely. So as long as when you take that number, that value that x is approaching, plug it in, you end up with a real number. That's your limit. There are a few exceptions to that rule, but those tend to be for more complicated functions, for things like piecewise defined functions or really complicated rational functions, things like that. So in part B right here, I have the limit as x approaches positive 2 of square root 3x squared minus 6. I'm going to try taking x equals positive 2. Let's plug this in and let's see if we get back a real valued answer. So here, square root of 3 times 2 squared minus 6, and we're just going to see what value we get here. So let's see, 2 squared I know is 4, 3 times 4 minus 6. This is radical 12 minus 6, which is radical 6, which if you want to give a decimal, that's fine. I think I'd actually prefer the radical answer. If you want a decimal approximation, it'd be somewhere, between 2 and 3? So square root of 6 will be just fine, though. And since that's a real number, that is my limit. That is my solution to this problem. Similarly, if I have a rational function here, this says limit as x approaches negative 2 of x squared over x squared plus 1. Let's take this number, let's plug it in, let's see if we get back a real number. So negative 2 squared over negative 2 squared plus 1. So here, negative 2 squared, I've got 4 over negative 2 squared. Again, I've got 4 plus 1. This is really 4 over 5. 4/5, it's a fraction, but it's a real number. So that means that value, this number, is my limit. That is my solution here. So this gives us a really, really quick way to evaluate limits of algebraic functions, and I think it's fairly intuitive, right? We just say, okay, most of the time, not always, but for most of the functions we deal with, the value of the limit is the same as the value of the function. Not every time, but for a lot of the functions that we'll be working with. So let's look at one more example here. Here we have r of x, which is a piecewise defined function. It says x squared minus 4, it's defined as x squared minus 4 if x is less than or equal to 2, and 4x if x is greater than 2. So here, now I want to look at the limit as x approaches 2 from the left-hand side, from the right-hand side, the two-sided limit, and then g of 2. So here, if I look at part A, this says limit as x approaches 2 from the left-hand side of g of x. For this, it might be helpful for you to actually go and think about what the graph of this function would look like. And we don't have to graph the whole piecewise defined function, but I do want to think about what it looks like here. So I just want a general idea. So we're sort of shifting gears right here at 2, right? It's defined one way when x is less than 2, and then another way when x is greater than 2. So clearly something's happening right here at 2. And so for x is less than or equal to negative 2, those are values that are over here, right? All of these values on this left-hand side are less than negative 2. That's defined by x squared minus 4. So this is defined by y equals x squared minus 4 over here on the left-hand side. That's kind of this whole area right here. Now, I don't need to graph that function, but I do know, hey, it's y equals x squared minus 4. But if I hop over to the other side, so if I'm on the right-hand side of 2, for values that are greater than 2, it's defined as 4x. So over on this right-hand side, it's y equals 4x. So that's this side over here. And so I could go and sketch the rest of this function if I wanted to, but I don't think I really need to here, because really all I want to do, I think the hardest parts about these are A and B, and then once we have those two, C and D will actually be, I think, a fair bit easier. So let's look at A here. This says, what's the limit as x approaches 2 from the left-hand side of g of x? So we're talking about the left-hand side right here, so that means we're talking about this side of 2. Well, it's defined on that side by x squared minus 4. So if you're not sure where to plug that in, I'm just going to take 2, I'm going to plug that into, well, how is it defined? y equals x squared minus 4. So I'm going to take 2, plug that into that part of my function, y equals x squared minus 4, so 2 squared minus 4. 4 minus 4 gives me 0, so the left-hand limit at 2 is equal to 0. Then if I wanted to talk about the right-handed limit, maybe we'll do that in green here. So if I'm talking about the right-handed limit at 2, well, how is that defined on the right-hand side of 2? Well, over here, this is all the right-hand side of 2. It's defined by y equals 4x. So I'm going to take x equals 2, and I'm going to plug that into y equals 4x. So here I've got 4 times 2 gives me 8. So the right-hand limit is 8. So if you've got the left-hand limit, you've got the right-hand limit. Part C, this is the part that should be the easiest, but I see a lot of silly mistakes on this all the time. Here, remember, if we scroll back to, I think it was 2 videos at the end of that second video, maybe it was the end of the first video, I don't remember. At some point, we said, you know what, in order for the limit to exist, we said, hey, the two-sided limit exists. We said if and only if, and I'm sort of using math abbreviation here, it says if the limits as x approaches c from the left of f of x equals the limit as x approaches c from the right of f of x. So, not 2c. So the two-sided limit only exists if the left and the right-hand limit are equal. So let's just check our answers here. The left-hand limit was 0. The right-hand limit is 8. The last time I checked, 0 is different than 8. So because they're not equal, this two-sided limit then does not exist. I don't need to show any work. I don't need to give any further justification. I've already justified it right here by showing the left-hand limit and the right-hand limit. A lot of students, what they'll want to do, they'll look for where is x defined, so where's that less than or equal to, or the greater than or equal to part. And when students think about that, they're actually thinking about this question right here. They're thinking about part D. When I say g of 2, that's where, okay, where is g defined exactly at 2? And that's when I'm going to be looking for that less than or equal to, or greater than or equal to. Really, it's the or equal to part that I am really interested in. So here I'm going to take 2, I'm going to plug it into this part of my function, x squared minus 4. We've already done that work, but just to be sure, 2 squared minus 4 gives me 4 minus 4 is equal to 0. So these are really good problems for making sure you understand not only piecewise defined functions, but you also understand how the two-sided limit depends on the value of the right-hand limit and the left-hand limit. We need to have a really, really good understanding of that if we're going to thoroughly understand limits, because this, I think, is one of the most important ideas here, is that the two-sided limit only exists if the left-hand limit and the right-hand limit are equal.